So today I'm going to be talking about electromagnetism. And what a lot of people don't realize is that electric fields and magnetic fields are actually deeply connected to each other. And this connection and relationship between the two is actually really useful for things like motors and electric generators, transformers, and actually most of modern day electronics rely on this relationship. So before we talk about electric and magnetic fields, let's just think about gravitational fields. If you have the Earth and you have some object here in space, well, the Earth's gravitational force is going to pull the object toward the Earth. And so we can draw a bunch of arrows around the Earth representing the direction that the gravitational force is going to pull objects. And objects further away from the Earth might experience a weaker gravitational force, so we might represent that as shorter arrows like this. You can represent electric fields in the same way. So I'm going to use a positive charge as my object or reference that's going to get pushed around. So positive charges are going to repel away from each other. So I might draw a bunch of arrows around this positive charge saying that positive charges are going to be pushed away. And you might draw a bunch of arrows pointing toward this negative charge saying that positive charges like this white one will get pulled inward toward this negative charge. So if you were to plot all of the electric fields of these two charges, it may look something like this. And all this means is that positive charges are going to follow along this path and get pushed by the electric force. Same thing can be thought of with magnets. Pretend I have some sort of object that is a North Pole only object. Now, in reality, magnets always have a North and a South Pole, but pretend you had an object that was only a North Pole. What's going to happen? Well, the North Pole of the bar magnet is going to push that North Pole object away from it. And the South Pole is going to pull the object towards it. So you might plot all of the magnetic fields around a bar magnet, and they may look something like this. All this is saying is that a magnetic North Pole only object is going to get pushed along the direction of these arrows and lines. And that's all pretty straightforward and intuitive, but something that you might not expect happens whenever electric and magnetic charges move. So the electric charge here is going to radiate electric fields E away from it. But whenever this object, say, moves to the right, and I'm going to represent that with an arrow and say V for velocity, for it moving to the right, a very interesting thing happens. It creates spinning magnetic fields around it that sort of get weaker as you get further away from the object. And this happens every single time an electric charge moves through space. It creates this sort of whirlwind of magnetic fields around it. In physics, we use B to talk about magnetic fields. The same is true for magnetic charges. Whenever a magnetic charge moves to the right with a velocity v, it actually creates spinning electric charges around it, or curling electric charges that get weaker and weaker as you get further away from the object. But these curling electric fields are in a counterclockwise direction around the object, while these magnetic fields are in a clockwise direction around this object. So we can redraw that here, and all this is saying is that this electric object right here in red is going to create electric fields as expected, but it's also going to create magnetic fields around it that curl around it. And here with this magnetic object, it's going to create magnetic fields around it. but it's also going to create curling electric fields. We can also think about this as if, well, what would happen if the charge wasn't there and we're just looking at the electric fields? So all of these red arrows are the electric fields, and if the object were to move to the right, well, from 1 second to the next, what does that move look like? So these electric fields look like this, but before they looked like this. So what's happening is that the electric fields are changing each second or over time. So when an electric field changes, we talked about how magnetic fields curl around it. So B for magnetic fields end up curling. And whenever a magnetic field changes, as if some sort of magnet or magnetic object were moving to the right, well, from 1 second to the next, the magnetic field changes. So B changes. What happens is that electric fields end up curling around it. And so we can actually write this in the form of an equation to sort of help us understand this relationship better. Notice though that I talked about how for a moving or changing electric field, the magnetic fields curl in a clockwise direction, but in the other case they curl in a counterclockwise direction. So we have to, in our equation, put a negative sign here, just meaning that it curls in the opposite direction. There's also one additional thing that we have to account for, because if you have a string of charges like this, you have a bunch of positive charges that are all moving together to the right so that you have some sort of flow of charges, you're going to still get magnetic fields in the middle and in the front. Well, why is that a problem? Well, the thing is that if these charges here are all moving from here to here, well, if you look at the center right here, the electric fields don't change. They're the same before and after. So we have to add this additional term. The fact that if you have a string of charges, we call that current, it also creates curling magnetic fields. So the middle here will also create curling magnetic fields. So this and this create curling magnetic fields. You don't have to worry about a string of only North Pole objects though, because in reality, magnets always have a North and South pole. So what's going to actually happen is that the front part of the magnet is going to have electric fields spinning around it like this whenever it moves, and then has opposite spinning electric fields on the south side as it moves. So these two equations define the relationship between electric fields and magnetic fields. And physicists like to define this in a different way with more formal math. And I'm just going to show it here so that if you ever see these equations, they make sense to you and aren't as scary, because a changing electric field means that the electric field changes from second to second, or in other words, it changes with time. So these strange looking D letters, that means just the derivative of the electric field over time creates curling magnetic fields, and we represent that as an upside down triangle, and X causes a curling magnetic field. In addition, also current, or a current density, J, also needs to be factored into there. And the same thing can be written for here, for the magnetic fields. So changing magnetic field creates a curling electric field. And this negative sign right here just indicates that it's going to be curling in the opposite direction from this equation. So if you ever look at these four equations, they may look scary because of all of these strange symbols and derivatives, but the concepts underlying them are not too hard. Here, whenever magnetic fields change, electric fields will always curl around them. Whenever an electric field changes, magnetic fields will always curl around them. These two other equations aren't too hard to wrap your head around either. All this means is that charges, like positive charges, have a bunch of electric fields coming away from it in all directions. What this equation means, the reason why this is equal to 0, means that every time you have a magnet, you may have electric fields coming out from it on the right. So these three arrows on the right are magnetic fields coming away from the north side. But you must always have three arrows coming back into the same magnet. So in other words, no magnet creates magnetic fields. It has fields coming from it that just come back into it. And so that's why this is equal to 0. These last two equations are more interesting though, because they talk about the relationship between magnetism and electricity and how they're so deeply interconnected with each other. And in my next video, I'm going to be talking about how we can use this relationship in making really useful devices for humans.